Now, since we're talking about words, Odin, I must say that when I was listening and watching, I didn't understand much. I'm not an IT person, so I focused on words that you used.
Yeah.
And one word that you used was foo.
Foo. Yes.
And for me, foo is obviously Foo Fighters. I have no other kind of associations. The other one was bool.
Yeah.
And for your information, if you say foo in Polish, that means jak.
Ah.
And then if you say bool, that means pain.
Oh.
And then you showed an explosion of an atomic bomb. And then you said something like nothing. So I thought to myself, has this guy got like a crime story or an apocalyptic story? Where he's going with this? So yak, pain, explosion, nothing. So I'm hoping the second part of your talk will be a little more optimistic for myself, at least, as well for the audience. Odin Holmes!
Okay. I will try and use words that have a positive Polish false friend.
Like szczęście, which is happiness.
Okay, what he said. I came here with a lot of my dev team, and I got a large Airbnb, and I previously thought that my dev team were uncloudifiable, but the Airbnb that we found was at the top of Sky Towers. So for the last couple of days, I moved my dev team to the cloud. So with Nokia's help, I removed the uncloudifiability. Okay, so here's where we left off. And because a few people asked me in the break to explain the pushback and modulo thing again, I figured that might be some commonality throughout the rest of the audience. What we are trying to achieve is we're trying to add a fixed parameter, a 2, as the second argument to modulo, right? Because modulo takes 2 arguments, and the first of those arguments is coming as the element in the remove if, because here we are a predicate, which decides whether this element gets removed or not, right? And we want to add as the second parameter to this function, a fixed parameter. First parameter is the thing coming out of the container, right? Second parameter, we want to add a fixed parameter of 2, right? And so ranges v3 have a lot more constraints than I do, because they have to worry about object lifetimes and the fact that you can't capture an overload set by reference and blah, blah, blah. But in a perfect world, one would be able in ranges v3 to say, okay, if I have a vector of int, and I just have one of those in there, right? I should be able to pipe pushback 2, right? And then pipe that into a call to the function modulo, right? So first stage, I have vector with just number 1 in it, right? And then my pushback. Second stage, I have a 1 and then a 2 as the second parameter. And then those get piped into the call to modulo, so its first parameter is 1, second parameter is 2. Right? This is the same kind of paradigm as that, just I can do a lot more crazy things than Eric can, because I don't have the constraints of having to work in the part of C++ that people have been making corner cases in for a long time. So this predicate will get a parameter pack with one thing in it, and that's going to be one of these guys, one after another. And we're going to push back an int of 2 to the back of it. That turns into one of these guys, and then the second parameter in the pack is 2, and that pack gets passed to modulo, and modulo's result is then either a 1 or a 0, because a modulo of 2 of any number is going to result in a 1 or a 0. That gets piped into is, right? And is will compare its fixed parameter of 1 to the parameter piped into it, and therefore return true or false based on whether modulo of 2 works, right? So this sort of tacit paradigm is a bit tricky at first, right? It takes a little bit before you get it. Now, in the second half of the talk, I'm going to convince you that the way we're doing things now in template metaprogramming is at least as complicated, if not more, in sort of standard library implementation and co. And that this has the potential of cleaning up some or most of that. Right? But I promised you we were going to look at toString, right? Okay, here's toString. Right? Here's the entire slide, which is a lot at this conference. You can actually fit a lot more on a slide at this conference than any other conference, because you have an awesome screen, right? So way up at the top, we have an if, right? Semantics of if underscore are, you pass me a predicate and a true case and a false case, and I'm going to, in the predicate, pass all the input parameters to the predicate, and it's going to tell me true or false, and I'm going to pass that same set of input parameters to either the closure in the true case or the closure in the false case, right? So if first thing passed to it is a predicate, so if it is 0, right, if it's the same as an int of 0, then we are going to pass, then we are going to just return, always as a meta closure that just always returns its fixed parameter no matter what you pass it, right? So if it is a 0 that is passed to us, then we are going to return a list with one element in it, and it's the character 0. Okay. In the other case, remember we got a number which we're turning into a string, right? And we want to build up this string recursively. So we need an empty container to begin recursion, right? Empty container, and then we're just going to keep pushing back the characters that we've rendered to this container as we go, right? So we're pushing back empty list, right? Then we have a while, right? The semantics of while are that we will just continue to execute our second meta closure as long as our first meta closure returns true, right? So we have now coming into our while a parameter pack of the number that somebody passed in, and the second parameter is a list, right? So we want to take the first parameter and test if it's 0 yet, right? Because we're going to be recursively dividing it by 10, and at some point it will be 0, right? Or not recursively, iteratively. It's actually recursive under the hood, but iteratively for the user. So we have our pack of number and list, and we will test if number is not 0, and if it's not 0, it will return true, and then we'll continue to this second parameter. So who here on the bash or on a shell knows what the command T means? Show of hands. Oh, good, 50% or so. That's pretty good. So the idea is, with pipes, real-world pipes, not our pipes, you can have a T-fitting, right? Where water can go like that, and water can go like that too, right? So out of one pipe, I make 2 pipes, right? And so this analogy, we have this analogy in Bash. It's not quite as powerful in Bash. In this case, we have our T-fitting will take a variadic pack of meta closures, and each one of those meta closures will get all of the input, right? And its last parameter, if you pass it n meta closures, then the n-1 will get all of, n through, 0 through n-1 will get all the parameters, and the nth will be the continuation, and it will get as its input pack the results of all of the other meta closures, right? So I have T, I have thing 1, thing 2, continuation. Thing 1 gets all the input parameters, thing 2 get that exact same pack of input parameters. They both return something. That goes into the continuation as its input pack, right? I don't remember what this is called in Haskell, but there is an equivalent. So we have in our T, we have a take index 0, right? So that's the number. We push back a 10, pipe that into divide, as in we take the input number and divide it by 10. Right? As the second parameter, we have an each. Each is kind of like a T, except that it has a variadic pack of metaclosures, the exact number of metaclosures that we're expecting as input parameters, and each metaclosure gets passed one input parameter in lockstep. So it's basically zip with functions. Right? So the first case, we're dividing it, we're pushing back 10, doing a modulo. So modulo of 10, right? And then we are pushing back the character 0. We're adding those together. So if you want ASCII characters, character 0 plus the number, as long as the number is smaller or equal to 9, is the ASCII character of that number, right? And then we're wrapping that in a list. And the second parameter of each, this was the one that's getting the list, right, as its input. It is just returning that list. You know, identity is all over functional programming. Identity is just a function that returns its input, right? And the last parameter each, the continuation, the thing we're piping it into, is join. So we made one list wrap number, and we have our list of all the other numbers that we've made so far, and we're going to join them together to one list, right? So basically, this is another way of pushing to the front of that list. And our continue is the metaclosure, which both of these T's values get piped into, right? So coming out of this is the number divided by 10. Coming out of this is the, oops, sorry. No. Yes, there we are back. Okay, so coming out of this top one here, we are getting the number divided by 10. Coming out of this each, we are getting the list of chars that we have produced so far with one more in it. And that will go into continue. And continue is basically just a marker to go back here and run this predicate again. Right? I probably should rename it because continue, normal keyword means some, you know, break out of the loop, right? Or I guess, no, it does mean continue in the loop. Anyway, so when this predicate holds false, right, then we are going to take the second parameter and we're going to unpack it, as in if it's in a list, if it's a list of parameters, we're going to take that list away and turn that into a variadic pack of parameters. And we're going to pipe that into whatever somebody put into us as the continuation, right? So we are a chainable operation here with the toString, right? Somebody passed in the next thing to do. Down here at the very bottom, we're piping all the rendered characters into the next thing to do. So now cue the unicorn. Right? This is, you know, crazy, scary, whatever. We're going to continue on a little bit down this path, and then I'm going to tell you what it's all for, right? I notice I actually have all this highlighted, which is, we already went through all of that, right? So if I have a toString and I have a modulo, what do I need to do? Obviously create the world's greatest fizzbuzz, right? So I make a sequence. For every number in that sequence, I call an if. I check if it's modulo 3, modulo 5. If so, return a type called fizzbuzz or fizzbuzz, right? In this case, it's either a fizzbuzz or a fizz. In this case, this actually should be a buzz. Ah, fail. Anyway, I made my slides too fast. But yes, so once we're done creating that, sorry, if it's not a fizz or a buzz or a fizz buzz, then we're going to render it to text, right? And we're going to push to front of everything a comma, and then, well, we're going to join everything, and we're going to drop off the first character, which is the preceding comma, right? And voila, we have a string of chars that in text says 1, comma, 2, comma, fizz, comma. And we can actually run this with 1,000 types. We can actually run this with 10,000 types, and it works and compiles and doesn't blow up and goes actually relatively fast, right? So this is, making the unicorny guy spin around. This is not useful. But if we look at sort of standard library implementation, this is the tamer standard library implementation. This is actually Absile, because the actual standard library looks even worse and it's harder to follow, right? So this is a constructor of optional. And this is all sorts of stuff depending on, trying to decide whether or not this thing should SFINAE, right? I mean, if you look at the implementation of the standard library, the vast majority of functions have some kind of enable if SFINAE thingy on them, right? This is everywhere. So, in sort of trying to be useful and not the dude spinning around in a unicorn costume, I've been thinking in the last year about this problem, right? Because this is something that users are not going to understand, and the reason why a lot of code bases don't have functionality in the sort of the same category as the standard library is because this is actually hard to do, right? And to prove that this is hard to do, this is from Absa, written by some of the best sort of expert-y people at Google, but you can still very much critique this code, right? If you look at like standard DK, that's doing a lot of work. That's doing more work than we need here. Absile conjunction, we can critique that, right? So let's but let's look at sort of what this actually does. Like, okay, who here in the audience would say off the top of their head, I know what this does? Nobody. Yes. But that's exactly the problem, right? I mean, you guys have been programming, and many of you guys have been using enable if and template metaprogramming functions, and probably 90% of you guys raised your hand for the enable if, and that means you work in this domain, right? And if you work in this domain and don't understand the implementation of a constructor to a not so super complex type, then we kind of have a problem that might be solvable, right? So, okay, enable if, we know what that is now, right? And then there's this huge gobbledygook here deciding whether or not we're going to enable, right? How many people here have seen conjunction and negation sort of in the wild? Okay, a few. Why do we need conjunction? It's and, yes. Why can't we just say this and that, this and that, right? Huh? Well, okay, this colon value and that colon value. The answer was because it's types, right? Sorry, I should be keeping up with my highlighting. I mean, why can't we just do this? Right? We have same kind of a thing, enable if, throughout the conjunction, throughout the negation, just did the bang here. The answer to this is because of SFINAE. So apparently we still don't understand SFINAE correctly. Problem here is, if this is an optional T, as in we are possibly a copy constructor, or in the overload set of the copy constructor, we better not test is convertible, because is convertible is implemented in terms of checking if we can copy, right? So if we were to just do this, this would give us infinite recursion because we ourselves are a candidate for the resolution of this type of traits, right? So we're way off in the weeds here. Sadly, this is the weeds, right? I mean, in a consulting role, I come into a lot of companies and look at their code base and what they're doing and whatever. And, Google has the AppSal team. Adobe, Facebook, some of these giant American companies have, teams that make libraries for people in the company. And it works very well. But most companies don't. And the reason they don't is because this is really, really hard, right? And conjunction, I mean, the reason for existence of conjunction is basically to be a lazy and, right? It's actually very hard to be lazy in metaprogramming. Lazy means short-circuiting, right? I mean, if the compiler knew that, hey, this thing's false, as in after the bang, this thing's true, right? Or this thing's true. This thing's true, so after the bang, it's false, right? So as soon as there's something false, it should short circuit because it's logical and, right? But the compiler doesn't know, or is not even allowed to, not instantiate this type just because in this particular case, I mean, that's not the semantics of C++, sadly. In our DSL, we can make up new semantics because we don't have any constraints, right? But as far as the performance of this whole thing, right? I mean, if we're thinking about ABSL optional, that's going to be all over your code base, right? I mean, it's not going to take a long time to compile, but in sort of a death by 1,000 cuts scenario, most of the time you are spending waiting for your compiler, you're waiting for things to SFINAE, right? I mean, this is really going to get me in trouble with the sort of upbeat nature of things to say most of your time you're waiting for things to die, but but you are. I mean, you're waiting for function overload candidates to be removed from the overload set, right? And all of the type instantiation and figuring outing and whatever of all of that. So not just from a writability and understandability standpoint, I would argue that there's also performance left on the table here. Because, I mean, if we want to get a domain-specific language of template metaprogramming accepted into the standard or upsell or something similar, probably not the standard because we're going to get new template metaprogramming before anyway, but it's not even going to be template anymore. But if we want to get a domain-specific language for template metaprogramming used in ABSL, it better not be slower than what they're using now, right? So do we even have a chance here, right? Can we beat hand-coded template metaprogramming written by experts, right, with a domain-specific language? The question is, what's the common case, right? I mean, we are being lazy, as in we are not executing all of this if this thing already matches, right? Is that laziness actually buying us anything? So if you think about what's the common case for the something like 16 constructor overloads of an optional, what is the common case, right? I mean, okay, maybe I have a foo and an optional. It's part of the overload set, and I'm calling, or in this case, decal typing. What type comes out of that function call, right? Well, this thing's got a templated constructor, and to see if it is part of the candidates, after name lookup and argument dependent lookup and all that stuff, I've got my candidates. Now I want to check if this thing is convertible to that thing. Well, then I've got to instantiate all the constructors and make sure they all SFINAE, and then I'm not a candidate, right? So the common case, in my opinion, by a long shot, is that all the constructors SFINAE, right? So we're really spending time waiting for things to die. So what's this, negation of is same in place t decay, this first test? Because this first test is certainly going to run, right? This first test is certainly going to run every time anyone calls a function that is part of an overload set where one of the parameters is an optional. And that's a lot of times, right? That's a lot of times. So for every unique type, I mean, once it's the same type again, then it'll be memoized, right? But a unique type is also that type plus const, that type as a reference, that type blah-de-blah-de-blah, right? So we're testing whether it's an in-place t or or it's the optional itself, right? As I noted earlier, the decay is actually a pretty expensive operation. Let's look at this. Let's look at this decay, right? Here we are back in the standard library. I told you it was uglier. So okay, we learned class template, right? Class template specialization because it's got the bracket, second set of parameters, right? So decay, if none of the other options match, the default case is remove constant volatile of the input type, and that's our type, right? The top level decay that we actually called, right? Top level decay basically only forwards to the underscore decay version with an is referenceable as its first parameter, right? So if it is referenceable, we get true. We do a bunch more stuff here. If not, we do that, right? And is array, there's actually a secret SFINAE test in there, right? So we're again waiting for something to die to test if something's an array, right? Remove extent, okay, that doesn't have a SFINAE test in it. Is function, that's a SFINAE test in there again, right? There's a lot of SFINAE testing here. Add pointer, remove CV, those go fast. So no matter what, with our decay, we are doing SFINAE, a lot of SFINAE somewhere, right? This is sort of the standard library SFINAE tests. We don't have to get into that too deeply. Other thing to note here is that we are actually instantiating a whole bunch of new types to test this, right? So there's, for every candidate that could possibly be convertible to an optional, you are instantiating hundreds of traits, and many of them you're waiting for them to SFINAE, right? So this is why this is somewhat slow, right? So if we look at negation of is same of optional decay u, right? Do we actually need that decay? Well, I'm not going to have a function pointer in my optional, right? Why do I need all that? Right? I basically just want to remove reference and CV qualifiers. This is what I actually want to do. And one could have written it like that, right? Question is, why do I care about volatile anyway? Right? I mean, optional is a type whose layout is not specified. Volatile means at that address something's weird, right? At what address if the layout is not specified? So arguably, we should deprecate a bunch of volatile, and there is a paper about that for C++20. We shouldn't need to support volatile in this context, but that's just saving us one type in our giant tree of types, right? These are the ones that are actually costing us even more, because there's a lot more SFINAE checks in those ones. And here's actually the next constructor in the list, right? Next constructor in the list is the exact same as the previous one. It just has a negation in front of this one, right? So in other words, no matter what happens, you're executing all of that, right? Unless it's an in-place T, in which case you aren't. But that only happens once, right? For all the other cases, you are instantiating every permutation. So the laziness is actually buying you nothing, right? It is only to make sure that we don't infinitely recurse. And the laziness is certainly costing us something, right? If we, writing it this way is actually considerably faster, but it's just wrong, right? So before we get into sort of what the laziness is costing us, what are all these type traits calls costing us? And is that costing us more than it really needs to cost us, right? Most type traits follow kind of this pattern where, I have my type trait is a thing, and it derives from either true or false, a true type, false type, depending on something. Right? So this is kind of the standard pattern for a type trait, right? And the underscore T version is defined by the standard to be the is a thing of T, it's : type, right? So for every type trait, no matter how I call it, either as an alias or normally, I'm going to get an instantiation of that type trait type, this guy, with parameter whatever you passed in, right? And remember, on the rule of heel, creating types is pretty far down the list. It costs something, because the compiler has to remember that for all of eternity, right? And every time you name a type, it actually has to go look, hey, has somebody actually already instantiated that yet? And if yes, okay, here's the instantiation. If no, I have to go build it and have to, allocate something and put it in a big hash table, right? So the more types you create, the slower it gets to create a type, because insertions into the hash table in practice are going to take longer and longer, and you're going to have more hash collisions because there is no perfect hashing of them. But for most type traits anymore, the compiler under the hood actually has an intrinsic, right? Underscore is same to you. Remember I told you don't double underscore any of your types or single underscore capital. It's because the standard uses them, right? And this guy is implemented in terms of, hey, that first type and that second type, are those pointers to AST nodes the same pointer, right? That intrinsic operation is going to go super, super fast, right? Problem is we have to create a type around it for no reason, really, right? It's just the way, this grew up over time, but this is sort of how the standard was standardized, right? So if I were to implement is same underscore T, I would say, hey, bool constant of the result of that thing. That bool constant, after I make true and false, I don't have to make any more, right? So for every possible type you can throw at this type tray, every possible combination of T and U, this one's doubly bad because it's not just for all the types in your program, because almost all the types in your program will eventually go into most of the type traits, right? So number of types in program equals amount of RAM, more or less, the type system has to hold. But in this case, we can switch them around. We have, a Cartesian product of all the types in our, right? But this doesn't actually have to make a type, right? Because, it's faster than looking up a type in a hash table to compare two AST pointers, right? Some of these other type traits is maybe comparing an AST pointer to, 10 different integral types, or maybe checking if it has some member function or whatever. But it's these intrinsics are quite fast. So why can't we just implement is_same underscore t in this way, right? The vast majority of use cases are just calling colon value on it, so its result is a bool constant. However, the way the standard specifies it, it's actually a is_same of t and u instantiation, which derives from that bool constant. And that is observable if you get really, really Machiavellian, because you could pattern match against the result of that. It would be the exact same thing you put in, so it would be a stupid idea to do that, but somebody might be, right? So they can't change it. I already had that conversation. It could also, have some implications on point of instantiation, because, we don't really care about that here. But in some other type traits, it could be dependent on point of instantiation. So we may need to rely on memoization, and because the intrinsics in the compiler are not part of the standard can't say that they must be memoized, even though they are, and so on and so forth, right? But we're a new thing. Standard doesn't know anything about meta closures. Let's make our own versions of all the type traits, make them fast. In fact, we could actually even make this faster, because we could pattern match against, hey, are you just an intrinsic under the hood? Let me call that intrinsic and just select answer A and B, right? Because in most cases, you were calling an intrinsic and then doing one of two different things depending on its result, right? So we can actually, in sort of a Haskell-y kind of way, look at what the user's doing and actually perform optimizations based on that. But that's getting a little ahead of ourselves. We can certainly do this. So, we can pipe that result into the next thing, and so on and so forth. This is the not specified, but you could implement it this way in library. So is this actually faster, right? Is this actually going to buy us anything? Well, yeah, runs a lot faster, right? I mean, it's almost 4x faster. So there is some potential to be had if we reinvent sort of the way things work, as opposed to the standard, right? If we add in some other things for reference, here we've added in, getting ahead of myself. What about memoization, right? This version is doing a bunch of unique types. Well, let's run the same thing 100 times, right? Or, memoization should kick in. Well, this is the memoized version, so this is looking up the type, and this is just doing the intrinsic, right? So we can actually measure that the intrinsic is faster than type lookup, right? I mean, I actually think that this benchmark might have been the reason why my last Surface died, because it was like full CPU for about 5 hours to actually get all the jitter out, because we're very, very close to the noise with these benchmarks, but Microsoft was nice enough to send me a new one. So we can do even more tests, and I guess I'm a little time constrained, so we won't get into these tests too much, right? But no matter how many we do, looking up a type ends up being slower than the actual intrinsic. And an alias call, right? So alias call to intrinsic is slower than type lookup in that case. So what is this conjunction thing, right? This is to be lazy. Can we optimize that at all, right? And to make this less hard on people, let's simplify this to this problem, right? Conjunction of is_same t in int, is_same t in bool, is_same t in char, is_same t in long. We remember that the is_same is one of the cheapest operations you can do, so that should be taking up little time. We should be getting quite close to the actual cost of the conjunction, right? So here we have lib C++ conjunction, and here we have the is same, right? So the conjunction is taking a lot more time than just the one is same, right? This is a, my conjunction, right? So we did save a little bit, right? The difference between these two is a little bit, unless you take the blue line and multiply it by 4, because we're doing 4 of these. So that's something like here. So my conjunction took this much time, and that conjunction took that much time, right? So we are at, we can implement a conjunction, which is, many x faster than the standard library conjunction. And that actually might be implementable, but why do we need conjunction anyway? Like the first time I saw it, I didn't know what it meant. I didn't know it meant like lazy and, right? Or the and that you were expecting, right? That's basically what conjunction means. So I would like to be able to do this, because that's, right? I mean, that's a lazy and, right? And this form of lazy and would support different operations here, right? In this case, if this is true, then we'll test that. If that's true, we'll test that. If that's true, then we'll test that. And if that's true, if this is true, then we're just going to be return true. And we left out all of the else cases, right? Because the else case defaults to an always nothing. If you leave it out, it will return a nothing, right? So if you want to test if something is a thing, and if it's not a thing, return a nothing, just leave it out. Here we have sort of our monadic concatenate to the end of things and say, okay, if this thing is a nothing, right? I mean, I stole this word from sort of monadic functions being proposed to be added to an optional from Simon Brand. Or else means, hey, if that's a nothing, use this type, right? So it's either true or it's false, right? And so here is, the real pendant to the conjunction, right? And with this one, I actually get way down here. Why did I get way down here? Because I'm using my DSL that just wraps the intrinsic, right? This was the cost of creating all those types, right? This red one. And this one down here, that's the cost of not creating any types and doing a super fast conjunction. So there is performance in some areas here, right? Now, if all I want to do is SFINAE anyway, right? If I want to SFINAE if this thing, if a nothing bubbles up to the top, rather than true or false and then piping that into enable if. Rather than call up here, I can just say maybe. The semantics of maybe are, call this thing, and if it results in a nothing, SFINAE. So all you raised your hands, what enable if does? Forget that, use maybe. Right? So what if I want to test if something SFINAE fails, right? I mean, in the standard library, we saw the handwritten true false blah de blah test, and it's actually interesting. It takes a different amount of time to SFINAE on different compilers in different ways, right? Maybe you're SFINAing in a class specialization, class template specialty. Maybe you're SFINAing on 2 overloaded functions. Depending on what your input is and depending on what you're doing, depending on what compiler you're on, will take a different amount of time, right? So why don't we generalize those SFINAE tests to say, okay, make an alias that does your thing that SFINAEs, right? Make an alias that says, I don't know, decal type of t.foo, right? If t has a foo, that will not SFINAE. If t doesn't have a foo, that will SFINAE, right? You make that alias, you pass that alias into my try, which is itself meta closure, so theoretically you could comma and then pipe that result into something. And the result of that will be either the result of this meta function or a nothing. Right? So we can capture SFINAE, propagate it through as nothings, right? And then out the other end, we can use a maybe, right? And the advantage of this is that under the hood, I haven't done it yet, but I have the potential of testing which compiler SFINAE is the fastest in which way, and using that kind of SFINAE depending on where you are, because I have the advantage of having one spot to specialize this, rather than the standard library, which does it all over the place, right? So coming back to, you know, our constructor here, well, you know, we could transform this thing into a, you know, this DSL, which is not super readable, but I would argue better than the previous version, right? And if you look at what's left over, if you will, of the things that we saw before, we have remove reference, remove CV. Pet peeve, that should just be a remove C, right? But, or remove const in that case. But that's going to be instantiated for your type anyway. For every type in your system, trust me, as long as that type has ever been part of an overload set that sees anything from the standard library, this is a memoized lookup. Happens once for every type that you have in your system. After that, memoized lookup, right? I think actually, yeah, I have them all highlighted. Is same, that's super fast, right? This basically, okay, SFINAE away, right? Always die is another, just a synonym for, or, you know, return a nothing, right? Is convertible, is constructible. Well, those are only going to get called if all this is wrong, right? But if we look back at you know, the previous version, right? We are essentially instantiating the same amount of type traits in both cases. Just you know, we are using intrinsics a lot of the time and saving some types, and we are certainly not decaying. And we are removing all the other overhead of being lazy. It's actually very hard to be lazy in normal, in air quotes, metaprogramming, right? In conjunction, in conditional. If you want to be very lazy in your conditional, then you can't say : type within the conditional. You have to say it after the result of the conditional, right? And so I decided, as sort of a thought experiment, to go down the road of, can I actually make boost.tmp always be short-circuiting if it can, and how much of a performance hit is that? And the gory implementation details is a talk for a future date in a probably much smaller room. But I was able to make it essentially no extra cost, except for a bug in Clang, but that's definitely a bug. So essentially no extra cost to make everything just automatically lazy, so it's the way you expect, right? So if you use and underscore, right, as our and, you can pass in a variadic pack of things, and they will be, the predicate will be applied to each one of them until one of them is false, and you're guaranteed to not apply any predicates again after that. If is lazy, right? It's only going to execute either the true path or the false path, right? Or underscore is lazy. Find if is lazy, right? All of these things are lazy at no extra cost compared to the fastest thing that me and Heel were able to come up with previously. I mean, no extra cost means sometimes we have 3% overhead or something, right? But you know, for this, it's within the noise, extra cost. So where are we going from here, right? I mean, I'm convinced that sort of the paradigms of the boost TMP library we'll be able to replace a lot of the day-to-day metaprogramming in a way that's as fast or faster, and is quite a bit more readable, right? I mean, notice in this, there are no template disambiguators, right? There's none of the : type or type name or any of that stuff, or conjunction that you don't understand. It's all a DSL. And it does take a bit to understand the tacit paradigm, but that is pretty much the only hurdle. Once you've got there, then... Right? So, as sort of future work, and I have done some work on this already, what about values, right? What about Hannah's domain? Well, if we apply sort of the tacit principles to operations on values, right, then basically what we want is a pack of values, a parameter pack. We can't generically capture a parameter pack in C++, right? So we have this pack underscore factory function that builds us a captured parameter pack, right? But as a concept, that is a pack of all the argument A's, right? And then we use the monad bind from Haskell, because somebody told me that's a thing in Haskell. And we apply just normal boost.tmp operations to that, right? So we can filter, I mean, if you are filtering in Hannah, the predicate on which you are filtering must be a compile time known predicate, right? Because otherwise you get a tuple whose allowed is unknown, and that needs to be known at compile time, right? So because this is, known at compile time, then we can just do type operations on these things, right? And if we want to use a predicate that is known at runtime, we can pass in a lambda, right? So transform over that, those filtered values, call this lambda for each one of them, right? We can push one to the front, right? We can do that, right? It looks a little bit like ranges, but we can push to the front. Anyway, we can fold over it with a lambda, right? And if we really wanted to, at the other end here, we could just pipe that into function call, or, standard library has something called standard apply, which basically takes, tuple thing, unpacks that tuple, pushes it in a thing. We have our apply, it's a pipe, right? This has the advantage of being able to use R-value references in a better way, because you can see where things are going. R-value references don't really work in Hannah. But it also has the advantage over Hannah of being much faster, because we can actually look down the chain of things that are happening in the future and do optimizations on what we're doing based on that, right? We also can use type-based predicates. Hannah has to use a lambda, a generic lambda, to be predicates, right? And another advantage over Hannah is this works in C++11. So I'm working on this a bit, and the reason why I'm working on this is I want to be able to take any input pack of parameters and programmatically decide how to change that with some transform graph into the parameters I need to call my function. This is called Production Guidelines by Sean Parent. It's a talk from many years ago, and I would like to be able to figure this out at compile time. So if you give me, my function takes height and width. This is the Sean Parent example. I should be able to also take a height and an aspect ratio, or a width and an aspect ratio, or 4 points, right? Or whatever is convertible to the parameters that I take in my function, and I should be able to describe that programmatically. I mean, the reason why we have in optional and in I think tuples even worse, it has something like 32 constructors, right? And the pattern, if you were to express that programmatically, what constructors does tuple have? It's relatively simple. It's just all permutations of a few things. So I would like to be able to express that programmatically so that I can solve a few other problems. And yeah, that's my talk. We can open it up for questions. I believe I have a red 4 minutes left.
Yes, questions, please. I mean, you know how to do it, right? You just raise your hand. Thank
Okay,
you.
one over here in the front.
That's simple.
Thank you for the talk. Could you please briefly describe the profiling workflow that you used for estimation? What is fast, what is slow?
Yes, this is actually some work that was done by Louis Dion while developing HANA. He developed a tool called Metabench, which basically makes two very slightly different versions of a translation unit and compiles them both and compares the time. Or makes many of them and compiles a bunch of them because it's obviously noisy, and averages them and spits you out some, these graphs that we've seen. This is not my work. This is Louis' work and some of Heel's work of explaining to me how to use it. So yes, stand on the shoulders of giants in that case. Yes, it's called Metabench. Metabench is both a website which compares the compilation speed of different libraries, and also a tool which is linked on that website as well. I think if you want to do that kind of profiling, then it's actually pretty easy to set up. You don't actually need Heel. You only need him if you're as bad at it as I am. I suck at tooling. Other questions?
Yeah, one over there.
How about compiler errors?
Compiler errors. Yes. Compiler errors are actually relatively similar in complexity to the compiler error that you would get through the standard library implementation. There's not a whole lot of difference there. We do, in the case of SFINAE, have give the user of choice of where they want a SFINAE def and where they want a hard error, which gives the user more control over how errors look, right? If they're not expecting SFINAE in some context, then they will not say maybe, and therefore you will get a hard error there rather than that thing being SFINAE'd away, some other thing maybe being taken, and so on and so forth, right? So, but in general, template errors are terrible, and this doesn't solve that problem.
I asked a question to Odin not long ago, and I asked him, why do you keep coming to Code Dive in Wrocław? All the conferences available. And Odin told me that it's vibrant, a lot of young people, and the final argument, I think, was that, and I quote here, that it is so fun. So the way he phrased it like that, there was a lot of O's. So
yeah. I like the local food and beer, too.
So, over to you guys. So fun. Ready?
So fun.
And again.
So fun.
And one more time.
So fun.
Yeah, but can you hear the fun in the word fun? It's not supposed to be like, it's your own funeral. So
you know, this so fun thing, it might be uncrowdifiable. But
Odin Holmes!